Okay, today we're going to look at the fundamental theorem of integral calculus. Now, let's just assume for the time being that I want to calculate this area here under the curve. So this is the curve y equals f of x, and I want to calculate this area here, which is shaded in, it's actually shaded in green on the diagram here. Now, we've had a couple of looks at how we might approximate this area, and one of those might be, for example, to use the lower triangles, and there's a couple of, sorry, not triangles, lower rectangles. And also we've looked at trapezia, and we've also looked at upper rectangles, but these are only approximates, and as a mathematician I don't want an approximate, I want the precise area of this shaded curve. And so what we're going to do now is look at creating some mathematics which will help us calculate the precise value of the area of this green shaded section. So what I'm going to do is, for the time being, I'm just going to assume that there is a function, which is the function capital F of x. Whoops, that's the function capital F of x, which can calculate the area between a and x. And what I mean by that is that there is a function that exists, we don't know what it is just yet. There's a function that exists that actually calculates this red area here that I've just shaded in. And so what this means is, with this function here, is that if I was to plug the number 2 into this function, I'm going to get the area under the curve between this arbitrary point A, which we don't know what that is at the moment either, and the point 2. And we're going to see how this is going to help us in just a minute. So how is this going to help us? Well, we have the function capital F of x here, which if I plug x into it, it's going to calculate the area from some arbitrary value a up to the point x, so this red area here. And if I was to plug a slightly larger value, or a value further to the right of the axis than x, into it, then it's going to calculate this larger area, which is the area again from the value a up to and including f of x plus h. And it should be reasonably obvious now that the difference between these two values, or this smaller area here and this larger area here, if I was to subtract these areas, or the difference between these two areas, again this smaller area and this larger area, the difference between these two areas is exactly the area that I want. And so let's look at this again. The area that I want, remember I started off wanting this green area here. The area that I want is simply the larger area, and minus the smaller area. And mathematically, remember that the function capital F gives me the area from the arbitrary value. The area that I want will then be capital F of x plus h, or the function of the function value for x plus h minus the function value for f of x. And that's going to give me the area that I'm after, the area under the curve. Now, of course, I still don't know what this function is, so I'm still not where I need to be. But coming back to what I'm after this area here underneath the curve, this green shaded area. That's the area that I want. And I now know that if I was to put the right-hand value here, x plus h, into my area function and take away the value here of x, I'm going to get the area that I want. But I still don't know what this function capital F is. So to do that, I'm going to need to do a little bit more math. Now, we've been doing approximations, and we've been looking at the approximations when we have a lower rectangle and when we have an upper rectangle. And so what I know now, or what I can see, is that this lower rectangle here, so the area of the lower rectangle, that's got to be smaller than the area that I'm after here. And the area of this upper rectangle, that's got to be larger. So I know that the area that I want is somewhere between the area of this smaller rectangle. This is obviously smaller, and it's the area of the upper rectangle. This area here is obviously larger, so the area that I want lies somewhere between the area of the small, or the small area, and the area that I want, which is the upper area here. Mathematically, how am I going to write this? So mathematically, I'm going to say that, well, the area of this small rectangle here is simply f of x times by h. Is got to be less than or equal to this function, f of x plus h, minus the function of x, and that's got to be less than or equal to f of x plus h times by h. And now I have some mathematics that I can start working with. And the first thing I'm going to do is I'm going to divide all of this by h. So I have that f of x, because the h's cancel out, is less than or equal to this big function f of x plus h minus the big function of x divided by h, which is less than, and again the h's here cancel out, it's got to be less than or equal to f of x plus h. Now I'm still not quite there, but because we've been looking at limits and so on in this particular chapter, what I'm going to do now is I'm going to take the limit of both sides here, or the limit of all of this. So the limit as h approaches 0 of f of x is going to be less than or equal to the limit as h approaches 0 of this expression here, and that's going to be less than or equal to the limit as h approaches 0 of f of x plus h. Now, what is the limit? Let's calculate the limit, or we should be able to calculate this limit. The limit as h approaches 0 of f of x just has to be f of x. I don't know what the limit of this is, so I'm going to have the limit here as h approaches 0 of f of x plus h minus f of x divided by h. And that has to be less than or equal to, well, the limit as h approaches 0 of f of x plus h just has to be f of x as well. And so now we have this very interesting situation where the limit as h approaches 0 of this function here has to be less than or equal to, greater than or equal to f of x, but less than or equal to f of x. So the only way that this limit here, this expression here, can be both greater than or equal to f of x and less than or equal to f of x is if in fact it is equal to f of x. So what I have now is that the limit as h approaches 0 of this unknown function, remember capital F of x is still unknown, and so all of the maths that I've done so far leads me to this interesting conclusion, is that I don't know what this function f of x is, or capital F of x is. This is an unknown function. However, if I take the limit as f of x plus h minus f of x over h as h approaches to 0, I'm going to be left with my original function f of x. And if you remember, f of x is simply this graph. That is the shape, or that is the function of this graph here. And what does that tell me? Well, it tells me that if I have this capital F function, if I have this function, and I was to differentiate it, remember this is differentiation. If I was to differentiate this capital F of x function here, I'm going to end up with the curve or the function that I wanted to find the area of, or the area underneath. And so if I have to differentiate this function here to get my f of x, then obviously if I've been given f of x, to get to this function here, that is simply anti-differentiation. Which is really, really interesting, because what that means is, coming back to my original question, I want the area under the curve. And all of that maths that I've just done in the early part of this video shows me that the area function, this capital F of x, if I was to differentiate this capital F of x, I'm going to end up with my curve f of x. So to find the area function, remember that right back at the very start where I said that I'm going to assume there's a function, f of x, which calculates this area from this unknown value a up until this unknown value x. If I was to differentiate that function, I'm going to end up with my curve function. And so therefore, to find that function, all I need to do is to anti-differentiate my curve. Differentiate my curve function.